Hello again. We are continuing our discussion of exponents and exponential functions by talking about rational exponents. Those are exponents that are fractions. So let's get started. We need to be able to convert between radicals, which are square roots, cube roots, and all of that, and rational exponents. Okay, so I can rewrite any square roots by using an exponent of 1/2. For example, if I have the square root of 8, that is the same as 8 to the 1/2. And root 29 is 29 to the 1/2. Those two things mean the same thing. Similarly, cube roots can be written by using an exponent of 1/3. So if I have the cube root of 57, I can write that as 57 to the 1/3, and so on. So if I have a fourth root, I can write it as something to the 1/4. You get the idea. Okay, if a base has an exponent, if the base has an exponent with it, then I need to change the numerator of the exponent. So it's not 1/2 anymore. It's not 1/3 anymore. So if I have the square root of 7 to the 3, that is 7 to the 3/2, not 7 to the 1/2. And if I have 29 squared, and I'm cube rooting that, that's 29 to the 2/3, not 29 to the 1/3. All right, we can also reduce the fractions too. So if I have 57 squared and I'm taking the fourth root of that, that is 57 to the 2/4. And I know that 2/4 is 1/2, so I can write that as 57 to the 1/2. All right, so evaluating these. To evaluate these, to evaluate a base raised to a rational exponent, I'm first going to look at the denominator part of that rational exponent, and I'm going to treat it as a root. And then I'm going to treat the numerator as an exponent. I could do it the other way around and I would get the right answer, but it's easier to go to smaller numbers and then bigger numbers rather than to go to bigger numbers and then smaller numbers. So let's look at 16 to the 3/2. Okay, the first thing I'm going to do is I'm going to take that 16, which is the base, and then look at that 2, which is the denominator of that fraction. I'm going to treat that 2 as a root, specifically a square root. So I'm going to find the square root of 16 first, and that is 4. Now I can look at the 3 in that exponent, the numerator of that exponent, and I can treat that as an actual exponent. So I will raise that 4 that I just found, raise that to the 3rd, which means I'm going to cube it, multiply 4 times 4 times 4, and that is 64. So my answer to 16 to the 3/2 is 64. Okay. All right, more evaluating. If I have 27 to the -4/3, because exponents can be negative even if they are rational. So let's do something else. Let's do 27 to the 1/3 and then raise that to the -4. I'm basically splitting up that -4/3 to 1/3 times -4. It's just another way of doing what I had already done. I'm just writing it out more clearly. So let's simplify what's inside the parentheses first. 27 to the 1/3 is the same thing as the cube root of 27, which is 3. Then I take that 3 and raise it to the -4. That is the same thing as 1 over 3 to the +4, which is 1 over 3 times 3 times 3 times 3, which is 81. So my answer is 1 over 81. All right. Similarly, if I have 8n to the 6 being raised to the 5/3, what I'm going to do is I'm going to take 1/3, put it inside some parentheses, or square brackets in this case, and then take that numerator of 5 and put it outside the square brackets, working with the denominator first and then the numerator. So if I have 8n to the 6 to the 1/3, okay, then 8 to the 1/3 is 2, n to the 6 to the 1/3. Remember, I'm multiplying those exponents, so 6 times 1/3 is 2. So I have 2n to the 2 inside the parentheses. I still have that 5 on the outside that I haven't used. But remembering what I learned in the first lesson, 2 to the 5th is 32, and n squared to the 5th is n to the 10. Okay, here's another example. If I have 25a squared all to the 3/2, what I'm going to do is I'm going to take the denominator part of that and move it inside some brackets and leave the numerator part of that 3/2 outside the brackets. So I have 25a squared to the 1/2 to the 3rd. Let's simplify what's in the square brackets first. 25 to the 1/2 is just 5. A squared to the 1/2 is a to the 1, or just a. And now I'm going to apply that 3 that's outside the brackets. 5 cubed is 5 times 5 times 5, which is 125. And a to the 3rd, or a cubed, is just a cubed. 81y squared raised to the 5/4 is going to be 81y squared raised to the 1/4, so just looking at the denominator first, and raise that to the 5. Okay, so 81 to the 1/4 is 3, and y squared to the 1/4 is y to the 1/2. I'm going to raise all of that to the 5. 3 to the 5th is 3 times 3 times 3 times 3 times 3, which is 243, and y to the 1/2 to the 5 is y to the 5/2. All right, so now let's look at some equations that I need to solve. These are exponential equations, and so the easiest kind you can solve is where you have the same base on both sides. So if I have 7 to the x plus 9 equals 7 to the 2x plus 1, I know that the terms are equal. The left side is equal to the right side, because that's what I was told. The bases are equal. They're both 7s. So what that means is the exponents must be equal. If I'm raising 7 to two different looking things, then those two different looking things must be equal. Okay, so I just look at the exponents. X plus 9 is equal to 2x plus 1. And now I solve it like a linear equation. Add negative x to both sides, so I get 9 equals 1x plus 1. Subtract 1 or add negative 1 to both sides, and I get that x equals 8. So the solution to that equation is x equals 8. It looks more complicated because it's got exponents in it, but now we have a way to handle that. Now, let's look at some tougher ones, because now I have 8 to the x plus 9 equals 2 to the 2x plus 1. What's different now is that the bases are no longer the same. Okay, so the terms are equal, but the bases aren't equal. So there still has to be a way to solve it. What I can do is I can rewrite 8 as 2 to the 3rd. So instead of 8 to the x plus 9, it's 2 to the 3rd to the x plus 9, and that still equals 2 to the 2x plus 1. And if I use my knowledge of exponents, 2 to the 3 to the x plus 9, those exponents get multiplied, so it's 2 to the 3x plus 27 equals 2 to the 2x plus 1. And now I have bases that are the same, so now the exponents are the same. And I just look at the exponents. 3x plus 27 equals 2x plus 1, and so solve it just like any other linear equation. Add negative 2x to both sides to get rid of the x's on the right, and I have x plus 27 equals 1. Subtract 27 or add negative 27 to both sides, and I get that x equals negative 26. So that's the solution to that, what we call exponential equation. All right, here's the last one. If I'm solving 9 to the x plus 4 equals 27 to the x minus 1, again, those bases aren't the same, and I can't raise 9 to anything to get 27, but I can raise both of those bases as powers of 3. 9 can be written as 3 squared, and 27 can be written as 3 cubed. So I can rewrite the original equation as 3 squared to the x plus 4 equals 3 to the 3rd to the x minus 1. And if I multiply those exponents, I get 3 to the 2x plus 8 equals 3 to the 3x minus 3. So now the bases are the same, so the exponents must be equal to each other, and that's what I solve. 2x plus 8 equals 3x minus 3. I will add negative 2x to both sides just to get rid of them on the left. So I get 8 equals x minus 3. And finally, I add 3 to both sides, and I get that x equals 11. So the solution to that equation is x equals 11. All right, so that was a lot of information. But if you have any questions, please let me know, and I will see you tomorrow.